I think before I start, I just want to say thank you. It's an honor to be invited to the grand opening of ICE. I want to thank the UN ECE for inviting me, and to talk about pre-mining methane drainage. I hope that as the first technical presentation that this would be noteworthy for you. I'm really excited about being able to show you some very interesting techniques and some of the approach that we take in pre-mining drainage in other parts of the world, and notably in North America. When we look at advances in pre-mining drainage, both from underground and from the surface, we find that most relate to being able to continue to displace conventional techniques with what we're calling directional drilling solutions. So that's really what I would say, we would say is really the biggest advance in pre-mining drainage. I'm not saying that directional drilling itself is a solve-all solution. In fact, I will show many coupled systems where directional drilling is coupled with other systems, particularly employed from the surface, for example. This presentation today is organized in 3 different sections. I'd like to go through initially to talk about considerations relating to approaching pre-mining drainage. I want to talk about some advances in directional drilling technology, actually 4 advances that I'd like to talk about, and then provide some examples of directional drilling solutions and real projects that we've performed. So when we evaluate an operating mine for methane drainage, the first things that we consider are the practices that are done today. What's being employed? What are the results? What techniques are being employed? What are the expectations and what the problems are? Then we look at the source of the methane emissions, because this is really the key, because if you can actually identify the source of the emissions and target that source, then that's really strategic in applying methane drainage, pre-mining methane drainage. We look at the source of emissions if they're from the exposed coal surfaces. We look at the characteristics of these emissions, because sometimes you can tell whether the emissions or the coal is actually permeability constrained or diffusion constrained. We look at other sources beyond the seam that's actually being mined, underlying seams, overlying seams, carbonaceous shales, for example. And I show here on the right side, this is the Pocahontas series. It's probably one of the most prolific CMM coal packages in the United States. Typically the P3, the Pocahontas 3 is mined. It's about 2.3 meters in thickness. And what I'm showing here, excuse me, what I'm showing here is really the zone of influence. If we longwall mine the P3, 120 to 140 meters up above, 20 to 40 meters below. Take a look at that P11. That's about 200 meters above the P3 seam. And I'm pointing that out because we're going to talk about that as well. We know that reservoir conditions significantly impact the effectiveness of pre-mining drainage. Pre-mining drainage relies on reservoir pressure reduction to initiate the desorption process. And this is best achieved in coals that have a very high intrinsic permeability and that are not diffusion constrained. So what we put together here is a table of the coal packages in North America that are the most prolific and where the commercial coal mine methane projects are or have been. This is the Pittsburgh seam area, so this is northern Appalachian. Pocahontas number 3, this is Western Virginia. Lower Hartshorn, this is in the Oklahoma, Arkansas area. And then the Blue Creek from the Warrior Basin. And then the double seam, which is in northern Mexico. All of these coals, Inseam boreholes are very, very applicable in all of these coals. And what we're doing is I'm comparing this to what I have Upper Silesian coal basin. This is from some information from the southern part of the basin. But if you look at the biggest difference here, it's depth in Poland versus the depth of the coals in North America. The permeability of coals in North America that are prolific for CMM production, especially commercial production, versus the permeability of the coals in the Upper Silesian coal basin. And then, of course, gas content. So we have some very high gas contents, some very permeable coals, and where Inseam methane drainage practices are very, very effective. So we use reservoir modeling, and what we do is we actually use this for planning purposes, and then also for optimization purposes. And what methane drainage engineers typically do is they use information in these reservoir models from actual reservoir testing. And then to make them really effective, to make them very effective, what we do is we match them. We history match existing production of water, existing production of gas, with what's predicted by the reservoir model. And only after that can you have confidence in your reservoir model, and then you can use it for optimization. But initially, we will use a reservoir model to determine, for example, what borehole spacing I'm going to need for Inseam holes. So what we're showing here is cross-panel boreholes drilled across a panel in a very tight coal and a very thick coal. This is in the Shanxi province, where the gas content reduction of about 50% occurs after 2 years, and that's predicted by reservoir modeling. And so we'll run these reservoir models initially to determine what our spacing is, borehole layout, to compare different Inseam methane drainage practices with each other, including vertical frac wells, for example, versus laterals. So now moving on to advances in directional drilling technology. There's really 4 that I want to talk about. The first is equipment, and this has really been a development over the last 3 to 4 years, and it's in really increasing the capacity of underground directional drilling equipment for extended reach. So what we've done ourselves is built drills, or have had directional drills built that with thrust capacities of twice what's commonly used. So typically, I would say since the early 1980s, we've been using drills, with 200 kilonewtons of push force, and now we're using drills of over 500 kilonewtons. This is the biggest drill, highest capacity directional drill in North America right now. It's in an underground coal mine for the first time. It was designed really for oil mining applications, but I'm proud to say that that drill is now actually in an underground coal mine in the United States. So what we've done is we've increased the thrust capacity, and we've increased the rotational torque capacity of these drills. And this is all really to extend reach and also to increase borehole diameter for effectiveness. The second part of the equipment side is really the downhole directional equipment and developing that equipment to be able to be able to match with the extended reach drills. So essentially extended reach directional drilling tools. And what we're talking about is we've had to increase the capacity of our fluid pumps. We've had to increase the capacity of our downhole motors, using larger diameter downhole motors as well. And then above all, really looking at the drill steel that we use and putting together a package that's suitable for extended reach. So right now, 2,000 meters is what we would call extended reach. There have been some directionally drilled boreholes underground that have been drilled in excess of 2,000 meters. And what this has done is also required us to change the way we communicate with our downhole steering system and to improve the performance of that system so that it can work at higher pressure and also with conductive fluids. The second advancement is really what I call the advancement in geo steering. So what I'm showing here is what we call our Directional Drilling Management System, the DDMS. It provides for an onboard computer, which provides for drill to plan, and it also incorporates a geophysical tool, several geophysical tools, but the one that we use mostly for geosteering is the Focus Gamma. And what we've done is we've developed a graphic user interface that will allow a driller to be able to better determine where he is placed within a coal seam. And so what we're doing here is we're taking some focused gamma readings, different focused gamma orientations. And you can see in this case, we're up closer to the roof. In this case, we're towards the center of the seam, and here the bottom of the seam. What the DDMS also allows is the processing of information from the drill itself, monitoring the drill performance. And this system really, the objective of this system is to be able to accurately place long directional boreholes in the mining seam and in adjacent seams, and to facilitate and expedite directional drilling, especially in thinner seams, with minimal deviation using horizon control, with minimum deviation using geosteering. The third development that I want to talk about is the use of magnetic ranging to intercept boreholes. So we've intercepted 2 directionally drilled boreholes that were developed from underground. We've intercepted vertical wells that were developed from surface and intercepted them from an underground well and the borehole. And then what we're showing here is actually intercepting a lateral with a vertical well. And what this does is it really provides some really new, unique methane drainage solutions, pre-mining drainage solutions. So in this example, what we did is we developed 2 boreholes in advance of this gate, set of gate entries. This is in a new mining area, and what we did is we took our underground drills and we developed a cut up on surface, and then we dropped angle and built angle and navigated using the DDMS, of course, to be able to get us right into the lower Hartshorn coal seam. We navigated the boreholes approximately 1,000 meters and intercepted a vertical well. So we intercepted the same vertical well with 2 laterals, about 150 millimeter diameter. And so now all of the water production to reduce reservoir pressure, since this is a virgin area, this is not mined yet, and also the gas production was from the vertical well. And so this concept really allows us to couple underground techniques with surface techniques. And then really the fourth advancement that I want to talk about is torque and drag modeling. And so this is something that we've taken from the oil field. It's a simulation technique, and what it really does is it helps us to better define our directional drilling capabilities. And so what we're doing here is we're looking at various configurations of drill steel size versus casing size at a certain weight on bit that we want to achieve, and using that to design, design a wellbore plan that's going to allow us to achieve the depth that we want to without any helical buckling or other issues that are going to cause us to limit and not achieve our objectives. So we know that Inseam boreholes are very, very effective because of the amount of surface area that Inseam boreholes expose. And then what I'm talking about is the natural fractures in the coal seam. So when we drill a very long 2,000 meter borehole in a coal seam, at our size, which is 96 millimeters, 600 square meters of surface, coal surface, are exposed to a wellbore. And that's very, very effective compared to a vertical well, for example, that just goes through the coal seam, which is 2 to 3 meters. What Inseam boreholes do is they provide for a reduction in reservoir pressure over a considerable distance, and provide, I think this is really the key here, they really provide for longer drainage times. And that's a key benefit. So some interesting applications here. This is a complementary technique. So this is the Consol mine in the Virginia Pocahontas seam. And what we did is we've directionally drilled in advance of mining back in 2006. Some very long boreholes. These are all in excess of 1,500 meters in length. They were quite prolific. They produced some of them as much as 40 cubic meters per minute at initial production. And what we did is we drained this area, we implemented these boreholes in 2006, and what we did is we navigated around vertical frac wells. And these vertical frac wells were placed in advance of our boreholes, but it was really just to reduce the gas content of this future area so that it can, for safer mining purposes. Well, here we are 10 years after that. And what's transpired really is what was thought is that the directionally drilled Inseam boreholes from underground would compromise gas production from the vertical frac wells. Well, that didn't happen. What the horizontal Inseam boreholes did was further reduce the reservoir pressure and increase the production from the vertical frac wells. And then what transpired is really a significant reduction in gas content, so much so that just in March of this year, or in April of this year, they achieved record production on this single longwall panel of 750,000 tons in 1 month. And then what's really interesting is that once development continued beyond the horizontal Inseam holes back into the frac well area, gas production started limiting developments. And this is in a coal seam that has a permeability of between 10 and 20 millidarcies. So some coals are very, very friable, and they really can't be directionally drilled. And in this case, what we do is, this is in the Warrior Basin, and this is an area also with prolific CMM production, or has had prolific CMM production. But in the past, the Blue Creek seam, which is very friable, was only able to be drilled using cross-panel techniques and using auger-flighted drill rods. And what they would do is they would drill very quickly into the coal seam, and then they would push in perforated PVC as quick as they could, and that would be the way that the gas content of the panel was drained in advance of mining. What we did is we came along using directional drilling practices, and we started developing a directional drilling approach using what we call a bridge seam. So this is the Mary Lee coal seam that's above it. This is only about 1 meter between the mined seam and then the overlying seam. And using the Mary Lee as the bridge, and it's competent, not as friable as the Blue Creek. And what we do is we directionally drill out over 1,000 meters, and then we come in and drop down into the friable Blue Creek seam to reduce its gas content. So this is a very effective technique. It's significantly more effective than the cross-panel boreholes. as far as recovered gas quality, and then also as far as the quantity that we were able to recover. We recover about 4 times the amount of coal mine methane or gas drained than with the conventional technique. In cases where coals are rotary drilled because of friable layers, directional drilling can be performed in specific partings that are competent. And so this is like using the bridge seam concept, but using the different coal layers as well. So what we're showing here is really in a friable seam where we would use perhaps even a very thin, 30 centimeter thick parting and directionally steer that to depth and then come through. And what this does is really breaks through some of these vertical permeability barriers in these coals, especially friable layers that you really can't directionally drill or rotary drill very well. But to come in and then use the competent layers as a bridge seam, use the DDMS and Geo Steering to be able to allow you to do that in very thin partings, and then come back and drill down through the friable layers, into the friable layers, through the vertical permeability barriers. This is another complementary approach. So in gassy coals that are tight, gassy coals that are well cleated, that I've seen that are cemented, and they're cemented with, let's say, they're cemented with clays, for example. You see that gas production from these coals, really doesn't happen unless mining-related stress changes take place, and that's when they produce, and that's when Inseam boreholes produce from these coals. And one of the techniques that we've used, and this was in an oil mining application, is we directionally drilled the most borehole in a single wellbore, 20,000 meters. This was for an oil mining application. But we actually intentionally intercepted vertical frac wells, and this was in an oil-bearing sand. And the reason we did this is because of vertical permeability barriers and permeability problems in that sand. But this is an example of using this technique in a tight coal where vertical fracs were intentionally created in the panel, and then perhaps these vertical wells could be used as gob wells in the future, but then directionally drilling and intercepting the fracs instead of like we did at the Consol mine, which was to navigate around the fracs. Here we intentionally intercept the fracs. And so here what we've done is essentially created a stress change and taken advantage of the production or the ability to produce the coal after the stress change. Long directionally drilled boreholes can reduce gas contents of adjacent seams, and then also reduce the gas content of adjacent seams, particularly in advance of mining, and ideally, depending on the vertical placement and the placement across the panel, to be able to use these boreholes as horizontal gob boreholes. One of the examples that I'm showing here is placing a directionally drilled borehole as a horizontal gob borehole to offset, for example, overlying galleries in mines, and using horizontal directionally drilled boreholes, perhaps higher capacity boreholes that are larger diameter, but intercepting a vertical gob well, for example. So what we're doing here is we're adding a horizontal leg to a vertical gob well. Reducing the gas content of underlying coals has been a big challenge, still is a challenge today, but with vertical well interception techniques, this is something that can be overcome. And here what we're showing is we're directionally drilling from the main seam down into an underlying seam. So this is going to be a seam that's going to contribute to gob gas. It'll be floor gas. It'll come up right on your longwall face from underneath and right behind your longwall into the gob. But to reduce the gas content of that seam in advance of mining, by drilling down dip and intercepting a vertical well. The vertical well could be used as a gob well in the future, for example. But the other point is this vertical well could be drilled from the mining level to this point, and the gas could be collected underground and not have to go up to the surface. So what we would do is we would drill a short vertical component and all of the water that usually impedes gas flow in these underlying wells, underlying boreholes, and the gas would be produced from the vertical section. So I want to show you something here that we did with this. Is that P11 seam. So it was 200 meters up above the P3. Was it going to contribute to gob gas? Well, it really depends on how those vertical gob wells that are implemented there at that Consol Buchanan mine are completed. But what we did is we identified vast regions where the P11 was undermined by the P3, and we came in from the surface. And so what I'm talking about here is targeting seams that have been relaxed by mining for CMM production. And so what we did is we came in from the surface, and we developed we dropped angle, built angle, got into this P11 seam, very, not even a meter in thickness, very gassy. But what's happened here is that this seam, because of the stress changes, down below by mining the P3, that the effective permeability of that seam was significantly increased. And what we did is we intercepted an old gob well and started producing the P11 over these mine tracks. And so what we're showing here is something that, well, we did this on surface, but can certainly be applied underground, especially in an area like here, where multiple seams are mined. Some seams are not mined because they're uneconomic, but perhaps they are affected by mining or relaxed, and the permeability, or the intrinsic permeability, the effective permeability of that coal seam may be enhanced because of de-stressing. The other thing, one of the things that Mr. Pilcher spoke about this morning was really the practice of piping explosive mixtures underground. And this is something that I've seen in different places. I'm sure Mr. Pilcher has seen it, but what we're promoting here is the ability to couple these systems to eliminate pipelines from underground entirely by coupling a horizontal system with a vertical system. And so what we're showing here is directionally drilling these long inseam boreholes in advance of longwall mining. And let's say we drill them up dip so that we're drilling them underbalanced, and then intercept a vertical well. And so what would happen is, in this case, the water production and all the gas production would be produced from the vertical well. There'd be no gas collection systems underground. And so it's a standalone system that could be implemented. And there are a lot of different, there are a variety of ways of doing this, different concepts of placing the vertical well in different locations and directionally drilling into the vertical well. But essentially minimizing pipelines underground. I think this is very key. And then we all know that mining plans really dictate the drainage schedule and dictate drilling locations. In the United States, high production longwalls, they really practice what we call just-in-time mining, or they try to practice that. And that's really that the development sections, as soon as the development sections are complete, as soon as the longwall panel is outlined, that longwall needs to move to that point, and the longwall starts. And so really, if you're looking at a cross-panel gas content reduction technique, you're not going to have a lot of time, a lot of drainage time. And so in some cases where mining schedules are very aggressive and you don't have a lot of access to infrastructure to drill from, what we recommend to do is to couple surface techniques with underground techniques. So this is a mine in northern Mexico that we've designed a degasification program from. Brand new mine coming in from some slopes, and what we would do is directionally drill from the slopes already and start degassing in advance of mining that seam. And then once we got underground, we would drill from underground as appropriate. But all of these other boreholes that we're showing here, those are all initiated from the surface. So coupling underground techniques with vertical techniques to effectively reduce gas content and allow high performance mining and schedules to be achieved. And then this is my final slide, but really shows the approach, what we are calling a mine appropriate approach, not using oil field equipment for surface to inseam drilling, but using equipment that's can be used on surface and underground. But what we're showing here is the ability to reduce gas contents over large tracts, intercepting vertical wells for gas production and water management. And this is what we call an early well intercept and an underbalanced approach moving forward. So I hope you found this presentation interesting, but in summary, I have a few points. Number one is the developments in directional drilling technology, really the extended reach, provides the ability for longer and larger diameter boreholes, offsetting overlying galleries, for example, for gob gas recovery, or long inseam boreholes for gas content reduction. Most importantly, what we're able to do with extended reach directional drilling is to reduce gas contents and provide for longer drainage time. And that's really key, is we're just trying to provide more time for gas drainage. The second point I want to make is the geo steering. And geo steering really provides the ability to address specific partings and seams, to use competent seams as bridges to be able to address gas content reduction of friable seams, and for placement of boreholes in adjacent seams. I also want to stress complementary techniques that use surface and underground. We saw with vertical well interception the ability to be able to provide standalone systems and minimize gas collection infrastructure underground. I think that's big progress. That's very progressive. And then I want to also show you the ancillary benefits of directional drilling, and this is really geologic exploration. And because generally when we're navigating in a seam, we're identifying the structure of the seam, and we can also quantify displacements, intrusions, and map that for the operator. And so directional drilling has some ancillary benefits besides gas drainage. In fact, I would say the majority of our directional drilling work, and we're running about 8 directional drills now in North America, is for geologic exploration and advanced mining, because we're able to provide this type of detail in between core holes that are spaced significantly apart. Anyway, thank you for your time, and I appreciate being able to make this presentation to you.